Hey guys, Mr. Bowman here. Today's learning objective is in white, and we are learning to calculate the number of trials and the individual probability in inverse binomial distribution questions. Before we get into it, let's quickly recap the binomial distribution formula, and that'll give us a good idea of how we can go about approaching inverse binomial questions. So the probability that random variable x occurs x amount of times is equal to ncx times the probability to the power of x times 1 minus the probability all to the power of n minus x. In that formula, we had 3 or 4 variables. So x related to the number of success that we're interested in, n that related to the number of trials, little p is the probability of the individual probability of success, and finally we're going to write big P down the end, and that's something new for us, and that related to the, we'll call that the big probability, or the probability of the group meeting that criteria that we're looking at. We'll leave it at big prob. Okay, so this formula is really important because what happens is normally you're given the number of successes you're interested in, the number of trials in the event, and the probability of individual success, and you'll use that to calculate the big probability. What's happening in inverse questions, so we'll change pen color just to demonstrate this, is in inverse questions, you're going to be given the big probability and given the number of trials, and you're going to be looking to work backwards to calculate one of the number of trials or the individual probability of success. And the big thing I want to emphasize for inverse Poisson questions, or sorry, inverse binomial questions, is that probability that only works if you know the probability of 0. If you can't figure out the probability of 0, you cannot figure out or inversely figure out the number of trials and the number of successes. Okay, so that's a lot of cool words and a lot of cool maths. Let's see what that actually means by an example. So I've got an egg container there. And let's say you've just gone to the supermarket and you've gone and bought a pack of 10 eggs. So a pack of 10 eggs. And as you're buying it, the supermarket checkout operator tells you that checkout operator tells us that 14.9% of these packs gets returned because of broken eggs. Because they have at least one broken egg. So we'll just change pen colors, but this is a pretty typical inverse question. Just noting, so a pack has 10 eggs, so we know that the number of trials is going to be equal to 10. So the checkout operator tells us that 14.9% of these packs get returned. And I just want to note these packs, that's the big probability because it contains 10 eggs. So that's the big probability. So what I'm going to write is the big probability of x being greater than 0, because they said at least 1, is 0.149. And this is actually enough information to inversely figure out the binomial or the inverse binomial distribution question. So down the bottom, we said we needed an x value, we needed the number of trials, and we needed the probability that x is equal to 0 to then be able to calculate the little probability, or in that case, the probability of an individual egg being broken. So hopefully you've made that distinguishment between the big probability, the probability of the whole carton meeting a certain criteria, and the little probability, the individual egg being broken. So x, so the first thing is we need probability of x being equal to 0, and that is actually going to be 1 minus the probability of being above 1. And that comes to 0.851. And that's because if you look at our number line 0, 1, 2, 3, 4, 5, 6, and so on, we've got this area. So we can do 1 minus p to find the probability of 0. We were given the number of trials, and we're also given the x value because the x value below is equal to 0. And that's enough information to figure this question out. So let's write down our formula. So the probability that x is equal to 0, well, that's going to be 10c0 times p to the power of x, which is 0, times 1 minus p to the power of n, which is 10, minus 0. And I guess the interesting thing about this formula, why it only works for 0, so nc0, well, that's equal to 1, and p to the power of 0, that is also equal to 1. So this part and this part actually just fall away. So that means we are left with 1 minus p to the power of 10, and we know that is going to be equal to 0.581. And if you use the solver function of your graphics calculator, you will be able to figure out or calculate the little probability, which was 0.0160, which was rounded to 4dp. So I'll just highlight that video. If you want to know how to use the graphics calculator to solve that last part, please watch the graphics calculator video. There is a big trick to this method in the calculator, so please watch that video. So what that means is that number down the bottom, if you pick a random egg from these 10 packs, the probability of that egg being broken is about 1.6%. And we figured that out because we knew there were 10 eggs per box, and we also knew that a box or a pack being returned had a probability of 0.149, and that let us do the rest. So probability 1.6%. So what we're going to do is we've just calculated the probability, but as I said, we can also work backwards to figure out the number of trials. So I'm going to pause the video. If you haven't got this example when they're working down, please do. I'm going to pause the video and I'm going to get into our next example. Okay, guys, we're unpaused. We're back into the next question. So we're carrying on with this theme. So in the previous question, we found out the probability of an individual pack or an individual egg being broken was 1.6%. So 1.6% of individual eggs breaking in the carton or in the pack. And we carry on with our discussion with the checkout operator, and they said, well, they're actually in the middle of redesigning the egg packages, and they're trying to change the number of eggs in each package to make sure the number of returned goods is below 10%. So to reduce the return rate to 10%. And I'm just going to clarify that 10% or less. So it has to be 10% or less. Okay, and from that information, we know that the little probability is 0.16. We also know that the probability of it being greater than 0, well, that has to be at a maximum 0.1. And because we're changing the carton size, we no longer know what n is. So if we're trying to calculate n, we need to know everything else. We need to know x, we need to know little probability, and we need to know the big probability of being equal to 0. If we have the other three, so these are the other three from our list below, we can then calculate n. We do know the little probability, 0.016, and we can calculate the big probability, 1 minus 0.1, which gets us to 0.9. And because we're dealing with x equals 0, we know that x is equal to 0. So that's good. We actually know all of the bits of information, so we're going to work backwards to find out n. So the probability that x is being equal to 0, well, that is going to be equal to ncx times px times 1 minus p n minus x. But I just want to remind us, if x is equal to 0, both of these parts do fall away, because nc0, well, that's going to be 1, and p to the power of 0, that's going to be 1. So that means we're left with the probability of x being equal to 0 is equal to 1 minus p to the power of n, and that minus x goes away because minusing 0 doesn't change the number. And just a note, that's the formula we actually use all inverse binomial questions. We actually will use that easier formula. So if you do memorize that, you can actually get into formula questions a lot faster than I did. So the probability of x being equal to 0, well, that's going to be 90%. And then we're going to go 1 minus 0.016 to the power of n. So that means 0.9 is equal to 0.984 to the power of n. And we can use our graphics calculator to remember to watch the graphics calculator video for the trick that will help with that question. And that means our n value, once we've got that from the calculator, is 6.53, and I've rounded that to 2 decimal points. Obviously, you can't have 0.6 of a egg, or sorry, 0.53 of an egg. So that means we've got to figure out, are we going to round up or are we going to round down? And what's going to happen is, so 6, and then between that we've got 6.53, and then we've got 7. So if we keep it at 6.53, well, that's exactly 90% completely. However, if we have more eggs, the probability of something breaking will be higher, which means the return rate will go down. So that might actually go down to 88%. And if we have less eggs, that might actually go up. So because of that, we need at least 90% correct. That means we can't actually round down in this case. So that means we do have to round up to 6 eggs. So that means I'm going to write it in that space in the middle up here. Our new carton size should include 6 eggs. There we go. And that there is our video on binomial distribution or inverse binomial distribution. The first question, we calculated the individual probability. The second question, we calculated the number of trials, or the number of eggs in our case. And just wanted to recap one key point. Doesn't matter what happens, this equation that I've just circled in green, that essentially becomes our inverse binomial distribution equation, because the rest of the binomial distribution equation falls apart because x being equal to 0 makes a lot of things equal to 1. So hopefully you found this video useful. Now let's get into heaps of questions.